All right. Fortunately, you can do these calculations pretty quickly. So again, we're considering Z8 now as a ring. Under addition mod 8, it's a group, an abelian group, in fact. Under multiplication mod 8, it's not a group, right? Rings are never groups under multiplication. If nothing else, 0 messes things up because 0 doesn't have a multiplicative inverse, no matter what ring you're talking about. Though if it is a field, what can we say about the non-zero elements? What's the definition of a field as far as the non-zero elements go? They are all what? Starts with the letter U. They're all units. They all have multiplicative inverse, inverses, except 0. 0 never does. And so rings are never, ever groups under multiplication. Fields are never, ever even groups under multiplication. But the non-zero elements of a field from a group under multiplication. Told you to make a multiplication table for Z8 star, which would be Z8, take away 0. This does not end up being a group, but you can still make a multiplication table for it. We should probably avoid calling it a Cayley table because it's not a group under multiplication. Identify the units in the zero divisors. Well, the zero divisors, once you've got this table made, are pretty easy to identify. Whenever you see the number 0 in here, the numbers in that row or that column are all zero divisors. So the zero divisors are 2, 4, and 6. Zero is never a zero divisor because, well, it's a special case. We say zero divisors are non-zero elements so that there's some other element such that the product is 0. So those are the zero divisors, 2, 4, and 6. And the other elements are not zero divisors. Are they all units? Are the non-zero divisor elements all units? Yep, I see people nodding, yes. They are all units. The inverse of 1 is itself. What's the inverse of 3? Also itself. What's the inverse of 5? Also itself. The inverse of 7 must also be itself, and it is. U of Z8 is the notation for the group of units of the commutative ring Z8 as a set consists of 1, 3, 5, and 7 under multiplication mod 8, dot mod 8. And it's isomorphic to what? What is this group isomorphic to? As a group under multiplication, ignoring addition. And in fact, it's not a group under addition, mod 8. It's not even closed. Z8 itself is a group under addition, mod 8, but not its group of units. They were only referring to multiplication. And groups of units of commutative rings, that is only referring to multiplication in the ring as the operation. What's this isomorphic to? We don't want to forget our group theory. It is isomorphic to U8. In fact, you could say it, maybe you could even say it equals U8 because it's the same set and the same operation. This equals U8. But what's it isomorphic to in terms of cyclic groups? Is it a cyclic group? Every element, every non-identity element has order 2. It's not cyclic. It's isomorphic to the external direct product of Z2 with itself. if R is any commutative ring with unity, then UR is called the group of units in R is in fact a group. Is in fact a group under the multiplication operation of the ring. Under dot from on. And in the case where we're talking U of Zn, units in the ring Zn, it is exactly the same as UN, the UN group. And in fact, you might even recall, we called that the group of units modulo n. Under multiplication mod n. It is under multiplication, not addition. So if we ignore the addition and we also ignore the zero divisors, just focus on the units, then we get a group under multiplication. Okay, that's something to remember. The most important kinds of rings for us, well, maybe we should mention a couple other things. A couple other questions. Is Z8 a field? No, it's not. 2, 4, and 6 are not units. Is Z8 an integral domain? No, it's not. It's got zero divisors. In fact, Zn is an integral domain if and only if n is prime. And in fact, Zn is a field if and only if n is prime. Zn is an integral domain if and only if n is prime. And Zn, in fact, is a field if and only if n is prime. But remember, fields and integral domains are not the same. Are they? Well, they are the same when the ring is finite. A finite integral domain is a field. Certainly every field, finite or infinite, is an integral domain. Certainly every field has no zero divisors. But there are some integral domains, and I'll talk about some examples here in a minute. There are some integral domains that are not fields. So the class of integral domains is bigger than fields. Every field is an integral domain, but not vice versa.
So for the zero divisors in this problem, would it be 2, 4, and 6 are all zero divisors?
Yep, 2, 4, and 6 are all zero divisors. Yep.
It wouldn't be that 4 is the zero divisor, or 4 is the only zero divisor.
Right.
And multiply by 2, 4, or 6.
Right. In fact, I emphasized on Monday that when you look at the definition of a zero divisor, it's symmetric in the A and the B. A non-zero element A is a zero divisor if there's an non-zero element B such that A, B equals 0, and therefore that also means B is a zero divisor. Yep. But yeah, finite integral domains turn out to be fields. The absence of zero divisors in the finite case implies all the non-zero elements are units. Yeah. And that's the proof of it. And it's fairly short, and it's something you should be able to reproduce. Not too hard. Just make sure you're careful in thinking about it and maybe rethink about it from time to time. Since ZP is a, well, in the proof that ZP is a field, well, they essentially prove it's an integral domain. They show it has no zero divisors. Make note of the fact that they use Euclid's lemma from chapter 0, the fact that if P is a prime, dividing A times B, then P either divides A or it divides B. Fact from chapter 0. But there are plenty of infinite integral domains that are not fields. Let's just summarize some examples here. Z itself, the integers, is an integral domain, but not a field. The only units of Z are plus or minus 1, right? Those are the only things with multiplicative inverses. The multiplicative inverse of 1 is itself, and the multiplicative inverse of -1 is itself. The group of units of Z is isomorphic to Z2. Interesting. And true, Z is an infinite ring that is an integral domain, but not a field. But its group of units just has 2 elements under multiplication mod 2, not mod 2, under ordinary multiplication, but it is isomorphic to Z2. The operation is ordinary multiplication. Remember that the Gaussian integers, Zi, set of all complex numbers of the form a plus bi, where a and b are integers, that had no zero divisors. We did talk about that the other day. That was where I was talking about setting up the system of equations and seeing that the matrix had a positive determinant in that case. In the system of equations that we set up, so it was a homogeneous system, and so it only had a trivial solution. This is an integral domain, ID, but not a field. What's its groups of units? What are the elements in here that are all complex numbers? Again, I is the imaginary unit, I squared is -1. What are the ones that have multiplicative inverses? Well, certainly 1 and -1 still do. And those are of this form. 1 is 1 plus 0i, and -1 is -1 plus 0i. The b in both cases is 0. I claim there are 2 more elements with multiplicative inverses here. Got a guess as to what they are? I and -I, yeah. The multiplicative inverse of 1 is itself. The multiplicative inverse of -1 is itself. However, the multiplicative inverse of I is not itself. It's the same as its additive inverse, -I. The multiplicative inverse of -I is I. Why? Well, I times -I is -I squared, but I squared is -1. I and -I in this multiplicative group have order 4 and are generators. You could also write this as this or this, and it's isomorphic to Z4. It's a cyclic group of order 4. Zx is the ring of all polynomials whose coefficients are in Z. As a set, you could write it like this. You could write, and it is actually somewhat traditional to write the polynomials where the powers go in ascending order here, but you don't have to. But I guess I will. A0 plus A1x plus A2x squared plus A3x cubed plus dot, 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 plus an x to the n, where n is some positive integer, possibly 0. I could write n is an element of z plus and also union with 0. And these ai's are all integers for I goes from 0 to n. You could just verbally describe this as the set of all polynomials of any degree. The degree doesn't have to be like 3 or something. It could be 4 or 5 or 6 or 2 or 1 or 0 if it's a constant polynomial. Although for technical reasons, the degree of the 0 polynomial is technically undefined. I'll explain why later. Could be degree million, a Google factorial, arbitrarily high degree here. But it is a polynomial, so it's not an infinite series. It does truncate somewhere, each element. It's got some degree, some highest power. You might remember from linear algebra that a set like this, where, well, whether n is fixed or not, also forms a vector space, polynomial vector spaces. In linear algebra, they were typically denoted Pn or something like that. Pn would be the space of polynomials of degree less than or equal to n. And that formed a vector space under addition of polynomials and multiplication of a polynomial by a scalar, by a number. And if the polynomial had a degree at most n, it was actually a finite dimensional vector space of dimension n plus 1. It's the same, well, okay, you can also talk about the space of all possible polynomials, which is infinite dimensional. As a set, this is the same kind of set, although we're only restricting ourselves to integer coefficients in this case, whereas in linear algebra, you allowed any real coefficients. I could allow real coefficients. I could consider Rx instead of Zx. But now we're thinking about addition of polynomials and multiplication of polynomials, whereas in linear algebra, you don't think about multiplying polynomials. This is a ring, in fact, a commutative ring with unity. Unity is the constant polynomial 1, which you technically shouldn't think of as the number 1. You should think of it as the constant polynomial 1, though it acts like the number 1 in many ways. If you graph it, it's a horizontal line, y equals 1, write the graph of it. That would be the unity. What are the units? What are the polynomials with multiplicative inverses? Well, if you think about it, if the degree of the polynomial is bigger than 0, if you have at least one positive power of x somewhere, that can't possibly have a multiplicative inverse, right? If you multiply two polynomials with degree 1 or greater, there's no way the powers of x are going to completely cancel to give you 1. Unless we were, maybe if we were modding, maybe some things could go away, mod by something. But here we're not doing any modding, so the units have to be constant polynomials. And in fact, since they're integers, there's just 2 units. The constant polynomials 1 and -1. under multiplication, and this is isomorphic to Z2. This turns out to be an integral domain. Turns out there are no zero divisors, but it's also not a field. The only units are plus or minus 1. What if I changed, what if I allowed real coefficients? What if I considered Rx as a set? It's the same kind of set, except you you allow the A's to be real numbers. N still needs to be a non-negative integer. It's a 0 there. Sorry, this is getting to be kind of a mess there. Each of these AIs is now allowed to be any real number, for I goes from 0 to N. Same kind of symbolism for a general polynomial of degree N. I'm not bothering to write that part again. But the A's themselves, the coefficients, are any real numbers. What are the units in that ring? That commutative ring with unity. 1 is still in there, the constant polynomial 1. Still, if you think about it, if the degree is 1 or greater, you can't have an inverse. So the units have to be constant polynomials. Which constant polynomials? Just plus or minus 1 again? No, the answer is bigger. Any non-zero constant polynomial will be a unit. The units of Rx is not equal to R star because constant polynomials are not technically numbers, but they're so close to being numbers, maybe we should essentially write equals here. I'll put equals in quotes. Equals R star, the non-zero real numbers under multiplication. I'm putting equals in quotes because constant polynomials, like say the constant polynomial 1/3, is not technically a number. It's a constant polynomial. Its graph is a horizontal line at 1/3. It's not really a number, but it's so close to being a number that maybe it doesn't hurt to pretend it's a number, a non-zero number. I do want the non-zero numbers, the non-zero constant polynomials. 0 still does not have a multiplicative inverse. Might be better to put isomorphic too, but maybe it doesn't hurt to say equals. They're so close to being numbers. They are effectively numbers. I'm not going to say any more about that. Well, that's an infinite group of units, but it's not the entire ring. It's not the entire non-zero elements of the ring, I should say. So while the ring is an integral domain here, and it's got an infinite group of units, it's still not a field. This is once again an integral domain, but not a field. Because any polynomial with degree 1 or greater is not going to be a unit. Any non-constant polynomial will not be a unit. So this is still not a field, in spite of the fact that R itself is a field. A plane R by itself is a field. Another example. What about, say, Z2x? Once again, to save time, I won't bother writing the stuff that goes in here. That's the same again. Z2x is the set of all polynomials whose coefficients are from Z2 and is still a non-negative integer. But now these AIs are each either 0 or 1. Each coefficient is either a 0 or a 1. That's a ring under polynomial addition and multiplication. Mod 2, when you mod the coefficients by 2 after multiplying. Is it an infinite ring or a finite ring? Are there infinitely elements in this or finitely many elements? N can be any non-negative integer. There's infinitely many elements in here, in spite of the fact that Z2 itself has only 2 elements. This polynomial ring is an infinite ring. N can be any non-negative integer. We don't want to restrict the degree because of the fact that we're multiplying polynomials. It's not like with the vector spaces in linear algebra, where we could consider polynomial vector spaces of a certain maximum degree, like degree less than or equal to 5 or something. We weren't multiplying back there. So the degree didn't get higher. We were only adding polynomials and multiplying them by scalars. When we allow multiplication, the degree can get higher, so we need to allow an arbitrarily high degree. I guess 1 is still a unit, the constant polynomial 1. But what about -1? Well, the constant polynomial -1 really equals 1 in Z2x because you got a mod by 2. There are only finitely many polynomials of any given degree in this. In fact, there's only 2 constant polynomials, 0 and 1. Though again, technically, for reasons I'll tell you later, the 0 polynomial technically has an undefined degree for some technical reasons. But they are both 0 and 1 are constant polynomials, and those are the only 2 constant polynomials in here. What are the polynomials of degree 1? Polys in Z2x of degree 1 and not 0 are going to be x and 1 plus x. Just 2 of them. Because things like 7 plus x are really one of these when you mod by 2. 7 plus x would be the same as 1 plus x. maybe that's not the best way to think of it. I'm restricting the a's to be in Z2 anyway. So I really shouldn't even bother ever saying 7 plus x. Though when we multiply, sometimes we have to do the modding by 2 in the calculation. So for example, if I square 1 plus x, I do need to square it in the usual way with FOIL. So as part of this calculation, I might write something like a 2 to help me realize, oh, I need to mod by 2 now. And so 2x is really 0x. And so this is really 1 plus x squared. Mod 2. Is it possible a polynomial of degree greater than or equal to 1 could be a unit? Is it possible when I multiply things that all the non-constant coefficients could cancel to give you 0? I don't know. At the moment, we have to explore that perhaps. It's not clear perhaps whether 1 is the only unit here. What's x times 1 plus x? That would be x plus x squared, which can't be simplified anymore. No modding by 2 to do. You might wonder if you did fancier things. You know, I don't know, 1 plus x times 1 plus x squared. Maybe we could get a bunch of cancellation. Maybe, maybe not. Actually, whether we get cancellation to a bunch of zeros or not does depend on the nature of the coefficients. Z2 in this case. And Z2 is a field by itself, just plain Z2, a 2-element field. What if there were Z4 where you've got 0 divisors? And I'll maybe let you do some exploring on that. Let's just go ahead and multiply these. So multiply 1 times every term, and then multiply x times every term on the right. These two things combine to give you 0x. These two things combine to give you 0x squared. 2x and 2x squared, mod by 2, you get 0x and 0x squared. So it simplifies to 1 plus x cubed. Strange, but true in this ring. Kind of fun, maybe? Yeah, we're kind of going to try to have some fun with this stuff. In fact, what I've emphasized is the main application we're going to look at of the class that I feel comfortable as semi-expert in is just dealing with factoring polynomials. Here we're not factoring them, then we're multiplying them out. But remember, factoring is going back the other way. So if I start with 1 plus x cubed, actually I'm going to typically write them from high degree to low degree, x cubed plus 1 instead. I can factor it as x plus 1 times x squared plus x plus 1 in this ring. I can do that factorization. I can't do that factorization if this was Rx. That kind of factorization would not be valid in Rx. But it is valid in Z2x. Turns out we'll be able to do polynomial division, long division. And if we're in something like this, Z2x, we got to think about modding by 2. In fact, let's go ahead and do an example. These are the most important kind of examples that we're going to be considering in the coming, what do we have left? 5 weeks, 4.5 weeks, something like that. What if we wanted to divide? So we're still working in Z2x. What if we wanted to divide a couple polynomials? say I wanted to divide, x to the 5th plus x cubed plus x squared plus 1 by x plus 1. Long division here. What kind of quotient and what kind of remainder might I get? Well, do the long division as you normally would, but just remember to keep modding by 2 for the coefficients, not the powers. Don't mod by 2 for the powers. Leave the powers as they are. X to the 5th is not the same as x to the 1st. If that was confusing to you. I'm not modding any powers, only the coefficients. The powers, in a sense, are just placeholders, symbols that, we usually think of variables when we graph them, but you don't have to think of them as really representing numbers at all. You could just think of them as just representing placeholder symbols. Algebraically speaking, that's effectively what they are. So what you do is you ask, what do I have to multiply by the highest degree term over here, the x by, to get the highest degree term over here? You got to multiply x by x to the 4th to get x to the 5th. Now take that polynomial and multiply times each term and put the answer down here. X to the 4th times x is x to the 5th. X to the 4th times 1 is x to the 4th. Subtract. I get 0x to the 5th. 0x to the 4th minus x to the 4th is negative x to the 4th, right? But wait, we got to mod by 2. Negative 1 equals 1. I'm going to go ahead and write x to the 4th here, but I really subtracted. 0 minus 1 equals negative 1, but negative 1 is 1 mod 2. So I really have a 1 times x to the 4th. I mean, it doesn't hurt to write minus 1 times x to the 4th, but probably good to get in the habit of doing the modding along the way. But we're only modding coefficients, not powers. Bring down everything else, the x cubed, the x squared, and the 1. What do I now need to multiply x by to get the highest power here? X to the 4th. I need to multiply by x cubed. Oh, fun with changing colors. Maybe I shouldn't have. Oh, well. Now multiply x cubed times each thing here. X cubed times x is x to the 4th. X cubed times 1 is x cubed. Subtract. Now you get 0 in both cases. Oh, I should have changed colors there to be consistent. Oh, well. I got 0. I didn't, by the way, the terms that have a coefficient of 0, you don't have to bother writing. I just did for emphasis. I didn't have to bother writing that at all. I also don't have to bother writing those two terms. I did for emphasis, but I didn't have to. What's the highest non-zero coefficient now? Highest power with a non-zero coefficient, it's x squared. What do I multiply x by to get x squared? I multiply it by x. Subtract. 0 minus 1 is negative 1, but negative 1 mod 2 is 1. Finally, x plus 1 goes into x goes into x one time, you might say. And I get an x plus 1 here for a remainder of 0. And if you think about it, the remainder either had to be just 0 or 1, nothing else, right? Mod 2. And the fact that it's 0 means that really x plus 1 divides x to the 5th plus x cubed plus x squared plus 1. I could even write something like this. I could say, therefore, x plus 1 divides x to the 5th plus x cubed plus x squared plus 1. And I could even write the factorization, x to the 5th plus x cubed plus x squared plus 1 equals x plus 1 times the quotient that I got up here. x to the fourth plus x cubed plus x plus 1. Kind of weird, kind of fun. I think it's fun. We don't fully understand everything yet, but yeah, these calculations can be done in this ring, Z2X. One, the number 1 is also a 0 of this polynomial. Wait, does that make sense to say 1 is a 0? 1 is a root. Maybe I should use the word root, though we won't avoid using the word 0. The 0 of a polynomial, also called a root of a polynomial, is something that makes the polynomial 0 when you plug it in for x, when you substitute. If I plug, well, the fact that I got this factorization means if I plug x equals 1 in here, well, right there I get 1 plus 1 is 2, mod 2 is 0. That one also gives me 0 mod 2 when I plug in x equals 1. 1 is a root of this polynomial here if I get 0 when I plug in 1 there. Evidently of multiplicity greater than 1, because this has got 1 as a root as well. I could divide this by x plus 1 and I would get a remainder of 0. In fact, you can do this stuff with synthetic division. I know I talked about synthetic division in my calc class. Haven't talked about synthetic division with you guys? I guess not. Seen synthetic division before? It's a way to divide some polynomial by a linear polynomial. And when you're dealing with something like polynomials in Rx, when you're dividing by something like x plus 1, you actually think of -1 as distinct from +1 as being the root. And you, in the synthetic division, you put a -1 over here on the left side of the synthetic division symbol I'm about to make. But here in Z2X, x plus 1 is the same as x minus 1, mod 2. So I'm fine with putting just a +1 in Z2X. And then you look at what you're dividing into. You look at its coefficients, and you put those down here as well, just as numbers, including any that are 0. X to the 5th has a coefficient of 1. X to the 4th has a coefficient of 0. X cubed has a coefficient of 1. X squared has a coefficient of 1. X, the linear term, is non-existent there. Its coefficient is 0. And then the constant term has coefficient of 1. And what you do with synthetic division is quicker than long division. You start by taking whatever number's there and you bring it down right there. Then the next step is to multiply whatever's here times whatever's there. 1 times 1 is 1. Put the answer here. Then you add, not subtract. Of course, mod 2, adding 1 is the same as subtracting 1, so it doesn't really matter here. 0 plus 1 is 1. Put another 1 there. 1 times 1 is 1. Put the 1 there. Add 1 plus 1 is 0 mod 2. Bring in mod 2 here. Multiply 1 times 0 is 0. Add 1 plus 0 is 1. Multiply 1 times 1 is 1. Add 0 plus 1 is 1. Multiply 1 plus 1 is 1. 1 times 1, I meant. Add 1 plus 1 is 0. What in the world am I doing here? This last number is always the remainder. And the fact that it's 0 matches the fact that we got 0 up here. Of course, in this ring, the only possible remainders are 0 and 1. In Z3X, the only possible remainders are 0, 1, and 2. if I'm dividing by a linear polynomial. If I'm dividing by some higher power, I could get a remainder that is also a higher power, higher degree, I should say. But if I'm dividing by a linear polynomial, first degree, the remainder has to be a constant. And in Z2x, that's either 0 or 1. It's 0, so I can say x plus 1 divides this. And notice that these numbers here, 1, 1, 0, 1, 1, match the coefficients of this polynomial there. 1, 1, 0, there's no x squared term. 1, 1. So this synthetic division is a quicker form of long division when you divide by linear polynomials. And I could continue it here. I know 1 is a root of this one. So I could do another synthetic division with a 1 here as well. Keep going. Bring down that one. Multiply 1 times 1 is 1. Add 1 plus 1 is 0 mod 2. Multiply 1 times 0 is 0. Add. Multiply. Add. Multiply. Add. I get another remainder of 0. And I have the coefficients here are 1, 0, 0, 1. That means this thing factors as x plus 1 times, that would be the constant term. This would be x squared, x cubed term, x cubed plus 1. And I know 1 is a root of that. I can keep going. Fun, fun, fun. 1, bring it down, multiply, add, multiply, add, multiply, add. I get another remainder of 0. And these coefficients, 1, 1, 1, tell me that I can factor x cubed plus 1 as x plus 1 times x squared plus x plus 1. 1 is not a root of that one, though, right? X squared plus x plus 1. If you substitute x equals 1, you'll get 1 plus 1 plus 1 is 3. Mod 2 is 1, not 0. If I do one more synthetic division here, I will not get a remainder of 0. I get a remainder of 1. So there's no more factors of x plus 1. But based on what I've gotten here, I can factor this. Well, I got a non-zero remainder. X squared plus x plus 1 divided by x plus 1 has a non-zero remainder. That means I can write the quotient here, looking right here, the quotient would be x plus the remainder 1 over what I was dividing by, so to speak, which was x plus 1. Now, I'm writing this as if it's okay to do in Z2x. It's technically not, because this is not a polynomial. It's better to write it this way, i.e., if you multiply everything by x plus 1, it's better to write, what am I trying to say here? Let me cross this off. What was I doing? I was taking x squared plus x plus 1 and dividing by x plus 1. It's better to write it as the quotient, which is x, times what I was dividing by, which was x plus 1, plus the remainder, which is 1. And that's obviously true. Scratch off that. Yeah, I wrote that wrong even, so ignore it. Okay. 1 is not a root of x squared plus x plus 1. Is 0? Is 0 a root of it? No, it's not either. The only two numbers in Z2 are not roots of this polynomial, x squared plus x plus 1. That means that polynomial, x squared plus x plus 1, cannot be factored in Z2x. We call it unfactorable, or a better word we use is irreducible. And this is going to be real big stuff for us, especially when we get to chapters 17 and 18, I believe. Maybe 19, somewhere in there. So what I'm showing you here is kind of a preview of that, but I think it's worth doing now as well. Our last few minutes here, 7 minutes. Let's just take a look at something you're going to be reading. The beginning of chapter 14. Title of chapter 14 is Ideals and Factor Rings. Factor ring. Is that like a factor group? Yeah, it is. Factor rings are similar to factor groups. The role that they're going to play for us is a little different, though. The role that factor rings are going to play for us is they're going to allow us to construct finite fields. Now, ZP, when P is prime, is a finite field. But it's not the only kind of finite field. Thinking about factor rings, where the elements are cosets, is going to help us construct more examples of finite fields. And those more examples of finite fields will help us in our quest to do factorization of polynomials. That is our main thing that we're aiming at here. That's why I spent so much time today on polynomial rings. To construct factor rings, you need an analog of a normal subgroup. Does that mean we need to call it a normal subring? Well, we could have, but we don't. The analog of normal subgroups in group theory are called ideals in ring theory. Who thinks of these names? Why an ideal? I don't know. It just seemed like an ideal name. Oh, sorry, bad joke. They do have ideal properties. That's kind of a bad joke too. What is an ideal? Here's the definition. A subring A of a ring R. Remember what a subring is. There was a subring test. I haven't talked about it in class, but you've read about it. A subring is an analog of a subgroup. A subring of a ring is a subset of that ring, this non-empty subset, that is also a ring under the same operations. And there's a subring test. Is it closed under subtraction and closed under multiplication? Ideals are subrings that are special subrings. We're only going to talk about what are called two-sided ideals. There are one-sided ideals as well, but it'll be simpler if we think about restrict our attention to two-sided ideals. Two-sided ideal satisfies the property that for every r, little r and capital R, the ring, and every little a in capital A, the ideal, both of these products, RA and AR, are in the ideal. These products are not necessarily the same. RA does not necessarily equal AR because the ring is not necessarily commutative. Remember, rings are commutative under addition. They are always abelian groups under addition, but multiplication is not commutative. prototypical example to have in mind when you're thinking about multiplication not being commutative is matrix rings. When you multiply two matrices, the order matters. So RA and A are not necessarily the same, but if A is going to be an ideal, they are both in A. So A is kind of absorbing an arbitrary ring element times an arbitrary element of the ideal. That's what it means to be an ideal. Now, it's not clear why that's a good definition. Just reading it. There is an ideal test. Remember the subring test that you read about says a non-empty set, I'll go ahead and call it A here, of a ring R is a subring if it's closed under subtraction. A minus B is an A whenever A and B are in A. And it was also closed under multiplication. But wait a minute, isn't that what these two things say in this ideal test? Closed under subtraction, closed under multiplication, isn't that what these say? They do imply closure under subtraction and closure under multiplication, but they imply a bit more. It's more that the A is closed under multiplication. It's hyperclosed or superclosed. What do I mean by that? It's more than closed. It's the R here is any element of R, not necessarily an A. As a set, A is a subset of R. You can take any element of A and any element of R, including things that are not an A. And if A is an ideal, when you multiply them, it'll be an A. Now, again, RA and AR could be different from each other, but if A is an ideal, they'll both be an A. Why is this important? Because it allows us to define factor rings. Just like normal subgroups allowed us to define factor groups. I mentioned in the lecture and even in here, factor groups are sometimes called quotient groups. Factor rings are sometimes called quotient rings. What are the elements of the factor ring? They are cosets. Left cosets, in fact, though written with additive notation, not multiplicative notation. So we write R plus A for an arbitrary left coset in the factor ring. And what the definition of an ideal allows us to do is to show that multiplication is, hey, there it is, well-defined. So the definition of an ideal is set up to make this multiplication well-defined, that you can prove it's well-defined. Whereas if A is a subring that's not an ideal, then the multiplication is not well-defined. Are there subrings that are not ideal? Well, yes, there are. Example 7 provides one example here of a subring that's not an ideal. I'll let you think about that. Have a good day.